Okay, so in the previous videos, the Navier Stokes equation was derived. So the next step here is to use the Navier Stokes equation that is here, that has already been derived, and to basically use it to model fluid by solving it numerically. So the idea is to take this equation, which is basically this is the change of the velocity field with respect to time. And then these are constants. That's a viscosity constant, and this is the rho, which is the density of the fluid. And then this is a viscosity term, which is the divergence of the gradient of u vector. I will go into this in more detail what exactly that means. And then the advection term, which is the u vector, the velocity dot product of the gradient symbol with the gradient operator, then acting on the velocity again, plus g, which is basically the external force term, represents the acceleration due to the external force, and then the final term is the gradient of the pressure. So the idea is to basically create this grid which is going to model the fluid. So the fluid will be modeled on a box. So the box is basically divided into cells, a grid of cells, like something like this. So these are all individual grid cells. And then in this direction is going to be the y, which is going to equal an index j times delta. This delta is going to be the spacing between the grid cells, and that's going to be delta in this direction and delta in the x direction as well, because it's the same delta. Square grid cells. And then this direction is the x direction, which basically equals the index I times delta. And then in a given cell, like, go change, do that color. So any given cell can have a velocity, and that velocity is equal to the u vector, and this is for the cell ij. So each of these cells is labeled by indexes, and this particular cell is going to be ij, and then this would be I minus 1j, etc. So each of these cells has some sort of velocity vector in it that might be pointing in a slightly different direction. So the fluid is basically defined on this, it's an incompressible fluid, so the fluid is basically defined on this grid by its velocity, u vector. And so what's going to evolve in time is going to be the velocities in each of these cells, and that's what this model is going to use the Navier Stokes equation to basically compute, or to model, is basically the evolution of these velocities with respect to time. So just to write this down, each cell has a velocity, which is u vector, and then whatever the index of the cell, ij. So the concept here is basically to solve the Navier Stokes equation by computing how this field evolves through different steps in time. So we're going to basically solve Navier. By computing the change in u. which is really the field. This is the entire field over the entire grid, so that's all of the individual U's. So the change in U for each cell. After a time step. And I'm going to define this time step as delta t. So the idea is to basically start with this part, go through each of these terms, and then see how they contribute to the change in u or change in t for each time step. So basically these terms are, the first term, the easiest term is the external first term. So G vector is acceleration, or whether it goes to, let me erase this. G basically causes the acceleration. And it's due to external force. And I'm going to call this acceleration du vector dt. And I'm going to call this force or external force. Or short, I'll probably call this force. So I'm just defining the acceleration caused by this guy as d, the partial derivative of u with respect to t with this notation force, to indicate that's the part of this acceleration due to the force. And then there's this term, which is the mu over rho. Divergence of the gradient of the vector. And this is basically, this is the acceleration du respect to t. But this is basically caused by the viscosity. So this is basically the force on each cell that's caused by the fluid around it moving and basically dragging that fluid in that particular cell, which depends on this, which is basically the viscosity constant. So if this was 0, then this term would disappear. But if there's viscosity, then it causes a force in each time step due to the viscosity. So this is the viscosity. Then the next term is going to, I can get rid of that. Down, okay. So the next term is this one, which is basically the u vector, is the velocity, dotted with the gradient symbol, u vector. This also causes an acceleration. And this acceleration is basically the advection. So this term causes a change in the again causes a change in the velocity field on each time step, but this term is computing the change due to the vection, which is basically the fluid moving through the cells, which will be covered in more detail later on. And I think this is actually negative. Should I put negative in front of it? Yeah, it has a negative in front of it. So basically adding all these up, there's basically a net change in the velocity field due to all of these terms. T. Say this is the net. You know what? I actually do not want to use these guys. I want to actually use the delta symbol instead. Which kind of a similar concept, but it's not quite the same thing. This is just notation. So the change in the velocity field for the time step is caused by each of these terms. So the net change in the velocity for the time step that's going to be caused by these terms is going to equal the sum of all these terms. There's the du, t. This is the force, and plus the delta u, t, is viscosity, and on top of that, finally that vection. So the equation is basically saying that it's going to predict basically a change in the velocity field for each time step. So basically, I'm going to define a V here. So this is a definition. V vector. This is going to be defined as the net change in the velocity field, basically per time step, due to all of these terms. So basically what the equation is saying, at each step in time, the equation is predicting that there will be changes in this velocity field due to each of these terms. So this is the Navier Stokes equation again. All of these terms are feeding into a change in u per change in t. So all of these terms basically cause a change in the velocity each time step. And the predicted change in velocity from these terms, ignoring the pressure right now, can basically be computed by taking each of these individual terms and basically multiplying it by delta t, is the basic principle. And that gives a new velocity. So all of these terms are basically trying to go ahead and change the velocity of the field. And so here's another definition. To define the V, I'm also going to define something called W. W vector. The W vector at t plus delta. Actually, I don't actually care whether I define a time for the W. But the W vector is going to basically equal the U vector at the beginning of the time step, which would be either t or t naught. I'm just going to refer to it as t right now, plus all of these the change in the U basically predicted by computing the changes due to the force, the viscosity, and the advection. Okay, so I just showed that basically if all of these, in a sense, force terms are computed, they basically estimate and change in U, change in the velocity field with respect to t, times the delta t, which gives a new velocity, which will, when added to the old velocity field, creates the field W. Now, technically, W could be the new U in some cases, and in some cases it actually is. However, in general, usually the divergence of W does not equal 0. So in general, divergence of W vector actually does not equal 0 in general. And if divergence of W does not equal 0, then it cannot be the next velocity field, because that would actually imply that the fluid was either generating itself or disappearing. So at least it would imply that it's not incompressible. So for incompressible fluid, the divergence of U has to equal 0, which means W cannot actually be U. So gradient dot U vector of t plus delta t, which is the velocity field at the end of the time step, has to equal 0 for incompressible fluid. So the reason this actually turns out to work, it turns out not all of the V actually contributes to the W. What that is, not all the vehicles contributes to the W, but not all of the V actually contributes to the to the new U. So not contributes. The V vector. Okay, so to see what's, oh, actually not to the V vector, but to the U at the new time. Okay, to see what's actually going on, a good way to do this is to basically look at the simplest possible example. So the example is a column waddle. So with the column of water, I'm basically going to draw this grid. So my sides, let me draw the grid cells. So here's the grid for the water. And then for this type of water, for this situation, let's have an open bottom. And for the column of water in general, the equation for the Navier Stokes just looks like this: G du vector dt equals G, which in this case is actually the acceleration due to gravity, for an over rho, gradient of the pressure. And for this case, I'll just assume that at the initial time at t0, the U vector is going to be 0. So U at start time equals 0, just define that. And so what's going to happen is there's going to be this column of waddle, and then it's going to start accelerating downwards. So for each cell, v vector ij is going to equal negative, in this case g will be the gravitational acceleration, and then y hat, I'm going to assume this is y direction, and that is x, times the delta t. So what the field now looks like, let's go ahead and, so each of these cells, the W is just going to predict that each of these cells have now moved downward a little bit. And they've all actually now all predictably moved downwards by the same amount. So just taking random cells, they just move downwards so far. So W ij equals, since this was 0, it's going to equal the same as Vij, so it's going to equal just the negative g, y hat delta t. Now it turns out in this particular model that actually the gradient of W is actually 0. Because this is just a constant, so the gradient of a constant is 0, and then in one dimension the velocity is 0, there's no x velocity whatsoever, and the gradient of a constant is 0. So for this solution, this actually is 0. So it turns out in this particular solution, this velocity is accepted and it just translates directly into a physical solution. So what actually happens here is W vector actually does in fact equal the U vector at the next time step. So T naught plus delta T. So basically this is, so this is just the waddle. The waddle starts to accelerate, and then it goes faster, it just goes out the bottom. And for this particular solution, the divergence is 0, so there's nothing wrong with that. However, the other case is the closed bottom case. Let's look at the closed bottom case now. So this is going to be basically the same, except the bottom is going to be closed. So again, we have this thing, have the grid, which isn't drawn that well, but I'll have to do. The grid of cells, this is an X, this is a Y, and again the V vector ij is going to look the same as it did before, since it's the same equation, negative the gravity times the y hat delta t. Again, I'm going to assume that the velocity was originally 0, so the W after at the end of this time step, Wij is going to equal g y hat t. So if I try to draw the V's, again the V's are all going to try to just go downwards. However, there's a special one and it's downhill. So there's all these V's that's simply trying to go down, so it would try to do the same thing, but what this is actually predicting is different, because this would be trying to predict that the waddle is obviously going to try to go out the bottom of the glass. The problem is that doesn't actually happen. So, and the difference here is that U vector, or U at I is going to be X, but J0 is going to be the bottom. This is the index 0 because the y is the j index, delta j again. So u at the bottom is going to be equal whatever velocity in the x direction there was, which doesn't really matter, and I is equal. But in the y direction, that's always going to have to equal 0. And so the consequence of this, the fact that this has to equal 0, means that the u vector at the next time obviously cannot equal the w. Obviously does not equal the w. Because down here, the u vector, this component of the w going downwards cannot exist. And also, and since presumably the velocity is, since this one has to equal 0, the w here, also would have as far as if this was simply set to 0, then that would solve the problem as far as the w, but the problem is at that point, then the gradient would be non-zero. So basically all of these things ultimately have to stop in order for, in this problem, they ultimately have to stop for the u to actually equal 0. What actually happens is, this is the water-glass now of u vector equals, at the end of the time step, actually has to equal 0. Because this is in fact the glass of water. So the question is, how does that actually come about? And it turns out what has already been shown is what actually stops the downward motion is actually the gradient of pressure. So what happens is these v's do not actually represent an actual motion in this case. What the v represents is an attempt at acceleration, but this attempt at acceleration is actually countered by a force. So it's more like so there's an attempt at acceleration, but then there's a force that actually balances that acceleration. And that force is actually the gradient of pressure. Okay, so what we actually have here is this v vector for each cell. So this is for each cell, it's going to be the same thing. So I'm going to write ij equals negative g gravitational acceleration times delta t. That would be how it would follow removing the step if it was on its own. So what this actually represents, though, is not a true acceleration. What it represents is a kind of pseudo acceleration that's actually countered by a force. In a sense, an attempt at acceleration. And call it acceleration in quotes. That is countered by a force. And the force that does this is pressure. Or more precisely, it's the gradient of pressure. So what actually happens here is dp with respect to y, which is the vertical direction, equals negative rho g, the gravitational force. And this was derived earlier because pressure equals rho g gravitational h minus y that was computed from the column of auto. That was done oil. So the change in the change in the u, change in u will change in t. Delta t is going to equal this term, which comes gt y hat. That is basically the v term minus the pressure term, which is basically the gradient of pressure, which in this case it only depends on y, because the x velocity is always equal. So the gradient of pressure times the delta t. The gradient of pressure is close in the y hat direction. So taking this negative rho g, the negative rho basically cancels this out, so it just becomes a positive g delta t, negative g delta t, both on y. So this works out to be 0. So this is actually, this is a specific example, but this is actually what happens in general. So this is not just for the water glass. So in general, when the estimated acceleration, which in the computation comes out as v, in general, when the v or part of v actually violates compressibility, or it tries to go illegally out the bottom of the glass through a barrier or something, the term that generally brings that back and cancels that attempt at acceleration is the pressure. So instead of having a velocity field that's actually violating compressibility, what actually happens is there's a surviving velocity field that maintains compressibility, and the part of the velocity field that basically violates compressibility or otherwise tries to go through a wall or something. These things are actually countered basically by the force of pressure, specifically the gradient of pressure. So I'm going to go back to just write that out. So if J violates wall equal to an kind of acceleration that is countered by a force, in this case, the gradient of pressure.